Hello Baselers, my name's Doug and I'm here to talk to you today about how we're migrating over 2,500 applications to Angular Ivy using Bazel transitions. I'll be telling you what the Ivy migration is, why it's so tricky, what Bazel transitions are, and how we're able to leverage them to scale this migration safely to so many applications. My name's Doug Parker. I'm a software engineer at Google, specifically on the Angular team. If you're not familiar with it, Angular is an open source framework for building high quality web applications, and I definitely recommend you check that out if you build web apps. Not only do we have support for Bazel, but we even use Bazel in our core GitHub repository, where external open source developers contribute their code to Angular. So we really love Bazel on the Angular team. But today I'm here to talk to you about a Google 3 migration. Google 3 is the mono repository which stores most of Google's internal source code. It's a massive Bazel workspace with millions of lines of code, and we want to upgrade it to Angular Ivy. Ivy itself is a new version of our rendering engine recently released by the Angular team. The specifics of it aren't too important for this talk, but it's a smaller, faster, and just generally better than our old system. It also makes puppies and kittens happy, so we're really pushing applications to use it. We've got over 2,500 Angular applications in Google 3, so we want to upgrade them to Ivy as quickly and easily as possible. Fortunately, Ivy itself is a re-implementation of existing Angular APIs, which means that applications generally shouldn't have to change their code in order to work with Ivy, making a migration much simpler since turning on Ivy is as simple as a flag flip. So if all we want to do is flip a flag, then this should be an easy change, right? Well, let's see how this might work. In Angular, we have our own build rule for compiling code. ng-module is our equivalent of TS library, Java library, or whatever your preferred language's library rule is. It's just our version. Ivy itself is a compiler flag, so it needs to be provided to the compiler action that runs under the ng-module rule. This means that the easiest way of enabling Ivy is to simply add it to our ng-module Starlark implementation, passing it as --ivy equals true to our compiler actions arguments. Since we're working in a monorepo and we only have one version of ng-module, if I merge this change, then all applications will immediately build with Ivy. That's incredibly easy, and it's also incredibly terrifying, for one simple reason that's best described by Hiram's law. Now, Hiram's law, if you're not familiar with it, it essentially states that if a system has a sufficient number of dependents, then eventually all observable behaviors of that system will eventually be depended upon by somebody. And while Ivy is theoretically backwards compatible, it is a re-implementation of these existing APIs. There are subtle differences in them that were never officially in the API contract, but applications have nonetheless managed to depend upon. With thousands of Angular applications, enabling Ivy would inevitably break somebody, no matter how backwards compatible we try to make it. If we enable this globally, as I showed a moment ago, then when one application has a production issue, we'll have to roll it back for everyone. And that can cause outages, increase friction for developers, negatively impact users, and it makes puppies and kittens sad, so we need to reevaluate our rollout strategy. Rather than roll out as one giant flag flip, we want to roll out incrementally. Specifically, applications should be able to opt into Ivy individually. Enabling Ivy for one application should not affect any other applications in the workspace. The Angular team should still control the default value, because with thousands of applications, asking them to migrate individually wastes a lot of time for everyone. We want to be able to just migrate those applications for them, hopefully without them even noticing. Even if this makes my job 100 times harder, it stops thousands of other teams from doing the same work, so it's still a huge win for the company. In order to safely flip this default value, though, we need to be able to opt out any applications that would be broken by Ivy. By doing so, we're able to safely enable Ivy by default for the vast majority of applications without causing any breakages. We'll also need a rollback strategy. If someone encounters a production outage when we flip this default value, they should be able to roll themselves back without affecting any other Angular application. There's also one other unique constraint that this brings up. Angular Ivy was originally developed with the expectation that an application is either entirely built with Ivy or not at all built with Ivy. You can't mix part of the application compiled with Ivy and part of it compiled without Ivy. That just doesn't work at runtime, and it's not the way the system was designed. What this means is that our builds need to be consistent. Either the entire application builds with Ivy or none of it does. And if you're experienced in Bazel, you might be thinking about how you could implement this rollout, so let's look at a couple approaches that immediately come to mind. Firstly, Bazel provides --define in order to specify custom build flags, where developers can add --define, some flag name, and then the value, and you can read this at build time in Starlark. We could use one of these to implement Ivy. The tricky part here is that developers must always provide this flag manually, so you have to remember to add it at the end of every Bazel build command. I don't know about you, but I can't remember to check the test pass before I send a PR for review, so I'm definitely not going to remember to do this. Alternatively, we could add this flag to our Bazel RC configuration file, so it's automatically applied on every build. That at least saves me from embarrassing myself in front of my coworkers. However, this also means that it applies to all applications in the workspace, so we can't apply this flag on an application-by-application basis like we really want to. The problem here is that these flags apply to the entire compilation, which is just too broad for our purposes. We want this to be application-specific, so this just doesn't quite work for us. Another way of implementing this flag would be to simply make it an attribute on the ng module rule. We can propagate this attribute to the compiler action and build and invoke that action with Ivy. This could be a little awkward, as we'd have to put Ivy equals true on all of our ng module rules, and that could be a lot. But we could automate this or use a clever macro. We could make that scale if we really needed to. So this actually sounds pretty good, but let's look a little bit closer. Let's say, as an example, we have a workspace with two applications. Each of those have a couple targets, and both of them depend on Angular Core. Core is our standard library core functionality. And for our purposes, everything depends on Core, because if it didn't, then it wouldn't be an Angular app and we wouldn't care to migrate it. So we can just pretend everything depends on Core. Each of these boxes is a different Bazel target, and they're all ng module rules. So each one has its own invocation of the Angular compiler and its own version of the Ivy flag. Since we're rolling out incrementally, we only want to change one application to use Ivy, and the other one should just be left alone. We can compile app1 as Ivy, but then leave app2 without it. But this immediately brings up a tricky problem, which is how do we compile Angular Core? Since it's just a regular ng module, there's nothing special about it. If we enable Ivy, then app1 will work, but app2 will break. And if we disable Ivy, then app1 fails, but app2 works. So we're really stuck between a rock and a hard place here. This is that shared library requirement in action. A library can be used by multiple applications using different values for Ivy, and the library needs to somehow be compatible with both of these. But that's just not how the compilation works. What we really need are two different builds of Angular Core, one that uses Ivy and one that doesn't. There are a few ways you can sort of make this work. You could split Angular Core into two targets via some kind of clever macro and make sure that all of these applications depend on the correct version. This actually becomes quite difficult for a number of reasons. For instance, keeping your dependency edges consistent between the two applications can actually be quite tricky. And not to mention, in your actual source code, if you're importing things referenced by the file name would then be changed, and so all your imports would be wrong, and you'd have to update those. So this actually becomes quite tricky very quickly. Ultimately, the problem here is that we're opting out individual targets, which is just too specific. It's kind of the opposite problem from what we had earlier, and it just doesn't support shared libraries in the way that we need to. So how do we want this to work? What I want to do is add Ivy equals true to the top level application target, just modifying it in one place because I'm a bit lazy. Then, when we Bazel build the first app, it should compile everything with Ivy for itself and all of its transitive dependencies, including Angular Core. However, when I Bazel build the second app, that should compile everything without Ivy, again for itself and all of its transitive dependencies. The lesson here is really that Angular Core doesn't care whether it's built with Ivy or not. It's happy to build with Ivy if that's what the application wants, and it's happy not to build with Ivy if the application doesn't. But is this kind of design actually possible with Bazel? You may be surprised to learn that the answer is actually yes. This is done with Bazel configurations and transitions, which are the way in which we're able to configure builds to provide this kind of functionality. First, I want to explain some rough definitions. Every target gets built with a configuration, and you can think of a configuration as the set of compile time flags and their values. Every target has a configuration which contains all of the flag values that target can read when it's executing its rule. Transitions are the means of transitioning the build graph from one configuration to another. This allows you to modify flags for a particular set of targets, effectively changing those flags dynamically based on the build graph. A target's configuration gets inherited by all of its transitive dependencies. This means that transitioning even a single target to a new configuration will also apply to that target's entire transitive dependencies. Those dependencies will also use the new flag values that were changed by the transition, and this is a really powerful feature which we'll be taking full advantage of for Ivy. So hopefully that gives you some rough idea of what these terms mean at an abstract level. So let's look at something a little more concrete to help clarify these concepts. First, let's consider a simple build graph that has three targets depending on each other. Each target has its own configuration and the set of flags that it compiles with. In this case, they are all using the default configuration, meaning that they use the default values for all of their flags. In particular, the test flag uses the default value of hello for all targets in this graph. we can introduce a transition to the bar target, which will transition its flag value from hello to world. What this means is that when bar executes its rule, it will see the test flag now has the value world. This transition has effectively changed the value of this flag for bar. Baz will also see the value world because it inherits this configuration from its parent. This means that all transitive dependencies of bar will see the new value of world. Foo, on the other hand, is unaffected, and it continues to compile with hello because it's sort of above all of this in the build graph. Now, that's a lot of high-level concepts, so how might we be able to apply this to solve our problems with Ivy? So let's revisit the original design we came up with a moment ago and how we can use transitions to implement it. We can add a new attribute called Ivy to ngModule and set it on app1 binary, the top-level target for that application. This will enable a transition which sets the Ivy flag on the configuration. This means that when we build app1, Ivy is transitively inherited for all targets in an application, as well as any shared libraries like Angular Core. When we build app2 binary, on the other hand, it is left alone because it did not set the Ivy attribute. So it does not have a transition, and app2 continues to build using the default value of false passed all the way down to Angular Core and builds correctly without Ivy. With this architecture, we're able to use transitions to isolate these applications from each other, while still using the correct Ivy flag for each application, even for libraries shared between the two. We're also working at the right level of abstraction now. We're opting in applications rather than individual targets like earlier, so this is much closer to what we originally wanted. By now you're probably sick and tired of box diagrams, so let's take a look at some of the actual code we would use to implement this. We start by defining a simple flag. We load this from Skylib, which is a library that has a lot of great Bazel utilities, flags being one of them. We pick some build file to define this flag, and we simply add bool flag as a rule. Since this is a simple build file, it actually has a target. This one exists at //angular::ivy flag. It's a little strange that it sort of has a position in the build graph and you can depend upon it, but that's actually how we're going to use it here. So now that we have this flag, we need to update our ngModule rule in order to depend on this Ivy flag. Because Bazel is Bazel, we need to explicitly declare all of our dependencies, and that does include flags. In this case, we're creating a new attribute which depends on this flag by default. This essentially means that all ngModule rules will now implicitly depend on this new flag. Finally, it's time to actually read this flag's value. In our rules implementation, we can use the context object to find the Ivy flag attribute that we just declared and read its value as a simple Boolean. For now, I'm just going to print it out with the target's name, but you can certainly imagine passing this flag to your compiler as an argument, or even choosing between two completely different actions. Maybe you want to have one action specifically for Ivy code and another action that invokes a separate compiler for non-Ivy code. And that's entirely possible with this design. Finally, when I'm able to build any ngModule rule, this code will execute and it will print out the flag. For now, building app1 binary shows that it and all of its transitive dependencies are built with Ivy set to false. So we successfully read the default value of this flag. Now we need to set it via a transition. Now what we want to be able to do is add Ivy attribute equals true to the top level ngModule rule and trust that all of its transitive dependencies will build with Ivy. We shouldn't need to add Ivy equals true to all ngModule rules because in a real app that'd be a lot, and frankly I just can't be bothered with it. Now I'm calling this one Ivy attribute. That's just to distinguish it from the Ivy flag that we defined earlier. It's just to drive home that these are two completely distinct Boolean values that are going to be working together to create the behavior that we want. We start by declaring an Ivy attribute defined as a simple Boolean and defaulting to false. This is because we expect applications to opt into Ivy. This works just like any other attribute you would use on a rule, and if you've done rules in Bazel before, you've done this countless times, and there's nothing special here. Now we get on to the actual meat and potatoes of this, the actual transition. We use the transition function in order to create a new transition, much like the rule or aspect functions if you've used those before. We need an implementation function that I'll show you in a moment, which will perform our actual business logic for this transition. We also need a list of input flags and a list of output flags. Because again, Bazel is Bazel, we need to explicitly declare our dependencies on everything. You thought we were going to get away with it for once, but that's just not the case here. The inputs are the flags that we want to read into our transition, while the outputs are flags we want to write to from our transition. In this case, we want to read and write the same Ivy flag, so that's the only one here. For the actual implementation, we define a new function that was referenced in the implementation parameter earlier. This function receives two parameters. First, it gets a settings dictionary, which contains the input configuration flags which we declared as inputs mapped to their current values. In this case, it would be a dictionary with the Angular Ivy flag mapped to whatever its value in the configuration that we inherited. This is essentially whatever the inherited value for ivy flag is. We also get an attributes object, which contains all of the attributes of the current target, such as name, depths, and most importantly, the ivy attribute. For the actual implementation, we start by checking if the user provided ivy attribute. And if so, we want to change the ivy flag and set it to true. In order to do that, we return the new configuration in the same format as the settings object. In this case, we just set / Angular ivy flag to true. Now, if ivy attribute is not set, we simply pass through or propagate the input configuration with no changes. This is essentially saying, just use the same configuration as my parent, I don't want to change anything. So transition logic is actually really simple, and all it does is read flag values and return new values. This whole talk is on transitions, and yet the actual code fits on one slide. I am lying a little bit. There's one more thing we need to do, which is that we need to simply add this to any affected rules. In this case, we need to update ng module and say that its configuration sets to the transition that we just created. This will execute the transition for all ng module rules. So now let's try it out. In order to switch an application to Ivy, all we need to do is add ivy attribute equals true to its top level ng module. Then when we build this application, we'll see that the binary, the library, and most importantly, Angular core, all successfully built with Ivy. All of these targets are in agreement about the Ivy flag. They will all build the same, and they'll be able to work together at runtime. Separately, if I build an entirely distinct application, like app2, which does not set Ivy, then we'll find that its binary, its library, and even Angular core are all built without Ivy. Again, they're all in agreement, and they're all able to build correctly and work together at runtime. So let's back up a little bit and review what we were originally trying to accomplish. We wanted to be able to opt in applications individually, and we've successfully done that by enabling Ivy for app 1, but by leaving app 2 alone. The Angular team also still controls Ivy attribute, and we can manipulate its default value. We can easily switch its default to true and make everybody build with Ivy when we're ready. Similarly, we can opt out broken applications by having them just explicitly pass Ivy attribute equals false, and they will be protected from the change in default value. We can also leverage this as a rollback strategy. When the default changes, everyone moves to Ivy, but if one application finds a production outage, then they can simply add Ivy attribute equals false, and it will roll them back without affecting anybody else. The other 2,500 applications still successfully roll out with Ivy. And in both cases, we're able to be consistent. Either everything is Ivy or nothing is, and we've successfully solved that shared library problem from earlier. So where are we right now? As of the time of recording, we have about 27 applications which have launched Ivy to production using our transition infrastructure. Currently, we're resolving a few of the remaining blockers and hoping to enable Ivy by default soon. One day, you may soon see that all your favorite Google Angular applications are suddenly running much smaller and faster, and all of this is enabled with the magical powers of Bazel transitions. So I hope this was informative and interesting, and I look forward to seeing what the rest of the Bazel community can do with transitions. Thanks for watching.